Hello, I'm going to be presenting a work by Itai Abraham, Filip Jovanovic, Mary Mahler, Sarah Michael John, myself, Gilad Stone, and Alin Tomescu about reaching consensus for asynchronous distributed key generation. Our work has four major components, four major protocols. We have an asynchronous distributed key generation protocol, an asynchronous consensus protocol, a weak verifiable proposal election protocol, and finally a verifiable gather protocol. And these protocols kind of feed into each other. For example, the proposal election protocol uses the gather protocol inside of it. In this talk, we're only going to talk about the distributed key generation, consensus, and proposal election protocols. And we're not going to talk at all about the gather protocol, even though it is of independent interest. It's a useful building block. So what is distributed key generation and what is it used for? Often in cryptographic protocols, we assume we have a PKI, a public key infrastructure. And that means, for example, that each party can have a public key and a secret key associated with it, which allows for encrypting messages and signing messages and things of that sort. That is useful, but that is often not enough for our purposes. For example, threshold signatures have been shown to be very useful in consensus and in many related tasks. And those need more structured randomness. A standard PKI kind of setup isn't enough to be able to use threshold signatures. We're going to talk a little bit more about what setup exactly we need for a threshold signature scheme. That setup can be done by central authority, for example. So we can have one party that kind of samples all the values, sends the values to all the parties, every secret key or public key they need throughout the protocol. And that could work. But for that, we need to have trust in that central authority. If we don't assume trust, we need to be able to do that, to achieve that same setup in another way. And that is what we call a distributed key generation protocol. It is also very important to be able to do that when the network is highly unreliable. So the kind of most unreliable we think of networks usually is having some Byzantine parties and having unbounded delays on messages, what we call asynchrony. So we want our protocol to be able to work in that setting as well, so that afterwards we can do efficient things while the network is still unreliable, or even later once it becomes reliable. In the previous slide, we discussed distributed key generation protocols, DKGs, in broad strokes. And now we want to go into a little bit more detail. And specifically, we're going to discuss DKGs for setting up threshold signature schemes. So when designing such protocols, we want to emulate a central authority that samples a public key, a secret key or signing key for each party, and a verification key for each party. It then sends each party the public key, their secret key, and all of the verification keys. Now, in threshold signature schemes, we want each party to be able to sign messages using its signing key, verify signatures on messages from other parties using their associated verification key. And if we only have these two functionalities, that's basically just a signature scheme. So in addition to that, we want to be able to take many signatures on a given message over some threshold and condense them into a single short digest that essentially proves that we had enough signatures on the message over that same threshold. We then verify that that is indeed the case using the public key. Now, if we notice here, this means we need some structure in the randomness. We need the public key, the signing keys, and the verification keys to be related in some way in order to be able to do that. The main result of our paper is an asynchronous distributed key generation protocol, which is resilient to fewer than n/3 Byzantine parties. The protocol requires a constant number of rounds of expectation and quasi-cubic number of words to be sent in expectation. In this case, on the order of n cubed log n. The current state of the art requires at least a linear number of rounds and at least n to the fourth words. This is a protocol by Kokolis Kogias, Malki, and Spiegelman from CCS 2020. This work uses cryptographic primitives from a previous work of ours, due to be published in Eurocrypto this year. We're going to talk about two cryptographic primitives. The first one is a DKG share generation algorithm. This algorithm allows parties to generate a small part of a DKG and then to input that part into protocols. The size of each share is linear in the number of parties. And this algorithm uses ideas of the scrape PVSS due to Cascudo and David from ACNS. Essentially, a PVSS is a secret sharing scheme which allows a dealer to generate a PVSS transcript. Parties can then check that it is indeed a correct transcript and receive relevant information from it about the secret sharing. The second algorithm is a DKG share aggregation algorithm. This algorithm allows parties to take a bunch of different shares and aggregate them into a single DKG transcript. This transcript is of the same size as the original shares, so in this case, linear in the number of parties. It is important when aggregating a bunch of shares into a single transcript to include at least one share from a non-faulty party. Otherwise, the adversary can completely determine the value of the key, and that means essentially that we need to have at least f+1 shares aggregated into a single transcript. The transcript also includes all the necessary information from the DKG, so parties can receive the public key, the set of verification keys, and their own signing key from the transcript. So how might we implement a DKG? The first thing I think of when I see this task is that parties need to agree on their output from the protocol. They all have to have a consistent DKG among them at the very end. So for example, they all have to have the same public key, the same set of verification keys, and each one has to have a signing key that's consistent with both. And to me, it sounds like we have to solve consensus somewhere in there. So now that we have this insight, a natural solution, at least in my opinion, for achieving an efficient DKG is executing the following three steps. In the first step, parties send DKG shares to each other. And as we know, those shares are of linear size, so overall, this round of communication isn't too expensive. Now, afterwards, parties need to accumulate at least f+1 DKG shares. As we've talked about before, we have to make sure we have at least one share from a non-faulty party in order to have secure keys. Now, thankfully, we can take f+1 shares and aggregate them into a single transcript of linear size. Otherwise, we might have had to work with linear sized lists of linear sized shares, and overall, that would be just too expensive to work with. Now, the final step is just reaching consensus on one of those DKG transcripts. And once we've done that, we're pretty much done. Now, it is important to note that we can only use a PKI throughout this protocol. We cannot use a specialized setup. So for example, we cannot assume we have threshold signatures because what we're trying to do is to set up threshold signatures using our DKG. Just as a reminder, a consensus protocol has the following three properties. The first one is validity. If all parties are non-faulty and they have the same input X, then they all output X. The second one is correctness. All parties that complete the protocol output the same value. This is the agreement part of the protocol. And finally, termination. If all non-faulty parties participate in the protocol, they eventually complete it as well. Now, we actually need a slightly stronger notion of validity, external validity, and for our purposes, it is enough to know that that means that every party outputs a valid DKG transcript. If we look at the correctness and validity properties, if parties don't have the same input, they technically could output anything. And we slightly make a stronger requirement that they output only valid DKG transcripts. The next big result we have in this paper is that there exists an asynchronous consensus protocol, which is resilient to fewer than n/3 Byzantine parties. It has linear sized inputs, which are externally valid. And in this setting, it requires a constant number of rounds in expectation and a quasi-cubic number of words to be sent in expectation. And the protocol only uses a PKI. A general approach for solving randomized asynchronous Byzantine agreement can be gleaned from Benor's protocol from 1983. That protocol is one of the first randomized asynchronous binary consensus protocols. And it can actually be thought of as a protocol with a virtual leader. The parties communicate, and they might ask the virtual leader for values, either 0 or 1 throughout the protocol. Now, the key insight is that throughout the protocol, the leader can be faulty, but it can never be silent. It always has to provide some value if asked for. The protocol proceeds in phases with a virtual leader in each phase. Now, if in a given phase, the virtual leader is non-faulty, then all parties terminate in a constant number of rounds, essentially in that phase. Otherwise, the virtual leader might be faulty. It might, let's say 0 to some of the parties and 1 to the rest of them. In that case, the protocol always remains safe. And by safe here, we mean that if a value x was output sometime in the past, then no other value y is going to be output in any future view. Now, for those well-versed in Paxos-like protocols, and specifically in the hot stuff protocol, these two properties are very common. In any given phase, in this case called views, if we have a non-faulty leader, all parties terminate in that view. Now, if we have a view with a faulty leader, we are guaranteed to at least maintain safety. We will never output a value different than a previously output value. We want to generalize the idea of a binary virtual leader to a multi-valued virtual leader, and we want to do that efficiently. The protocol that achieves that in our paper is the weak verifiable proposal election protocol. In the beginning of the protocol, parties input some value, and then we sample the index of one of the parties that actually input something into the protocol. Afterwards, we send that party's input to all parties. Now, the protocol is weak and verifiable. So what do these words mean in this context? The protocol is weak in the sense that there's only some constant probability alpha that all parties receive the input of some non-faulty party. With the remaining probability, 1 minus alpha, parties might receive a faulty party's suggestion, or alternatively, just different parties could receive different values. The protocol is verifiable in the sense that parties can prove to each other that they actually received a given value from the protocol. So when some party receives a value v, it also receives a proof pi that this is their actual output from the protocol. Another result of our paper is a weak verifiable proposal election protocol. The protocol has inputs of size O of n. And in the paper, we construct a weak verifiable proposal election protocol, which requires a constant number of rounds and a quasi-cubic number of words. We have at least a 1/3 probability of succeeding, so alpha is 1/3. And this protocol uses the gather protocol and extends the techniques of the Canetti-Rabin asynchronous Byzantine agreement protocol. So now we're ready to talk about the no-waiting hot stuff protocol, or consensus protocol. This is a view-based protocol. And unlike vanilla hot stuff, in each view, we have a virtual leader, which is implemented using the proposal election protocol. In the beginning of each view, parties input proposals into the weak verifiable proposal election. And in this case, their proposal is supposed to be the value that they would have sent to everybody else as non-faulty leaders in the hot stuff protocol. As we know, we have a constant probability, in this case, the third, that the proposal election protocol chooses one non-faulty proposal and sends it to everybody. With the remaining probability, in this case, 2/3, each party receives some value. We don't know if it's an honest value. It might be a value from a faulty party. it also might be the case that different parties receive different outputs from the proposal election protocol, but we know that every party receives something. And then afterwards, parties send their outputs to each other, provide the relevant proof, and essentially continue with the regular hotspot protocol. The only difference is that if parties see faulty behavior, in this case, either invalid messages from faulty parties or equivocation, and by that we mean two different parties having two different outputs with proofs from the proposal election protocol, then they inform each other, and then they can continue to the next view. Now we're going to talk in very, very high level about why this protocol should work. And for more details, I urge you to look at the full version. We're going to divide our discussion into a discussion of safety and a discussion of liveness. So for safety, we achieve a property that if a non-faulty party commits in a view V, and by committing we mean is about to output a value, then no other value receives enough support from non-faulty parties in that view or in any later view. And if no other value receives enough support, then it won't proceed to later stages of that view. And that means that parties won't output that other value in those late stages. This property is shared with the hotstuff protocol and is achieved using the key and lock mechanism of hotstuff. Now, we can look at the different possible outcomes of the proposal election protocol. We either have a unique proposal elected, either faulty or non-faulty in this case, in which case that is the same as having a single leader in that view. And the hotstuff protocol knows how to deal with that. If we have a single leader, either faulty or non-faulty, we maintain safety. The only behavior that can happen in our case and can't happen in the original protocol is having two different proposals output by two different parties. Now, that is akin to having two different leaders in the hotstuff protocol. Now, this is actually not an issue because that is the same as having an equivocating virtual leader. And a Byzantine leader can equivocate, and the hotstuff protocol knows how to deal with equivocating leaders, and thus we can maintain safety in this case as well. When looking at liveness, we can notice that the virtual leader implemented by the proposal election protocol always provides values for parties. Now, the original hotstuff protocol needs to use timeouts because leaders might not send values. Since this isn't the case, we actually don't need timeouts in our protocol, which is crucial in an asynchronous setting. Now, when looking a little bit further, our proposal election protocol has two different possibilities. Either a unique honest proposal is elected, and in that case, that is the same as having an honest leader that sends the same proposal to all parties. And in that case, parties advance through the view, and we know that they eventually agree on the leader's proposal and terminate, because that's what happens in the hotstuff protocol. On the other hand, if that isn't the case, then different parties might output different values, or alternatively, all output the same value, just not necessarily the value of an honest leader. In that case, we know that parties can prove both equivocation and the fact that the proposal is faulty to each other, and we can always make progress. They either manage to continue through the view, or eventually they'll see that one of these events has taken place and will continue to the next view. Now, it is important that parties can't actually prove to each other that one of these two things happened when a non-faulty leader is elected. Otherwise, the Byzantine parties might make us advance through views even with non-faulty leaders, and that is indeed not the case in our protocol. In conclusion, in our paper we present 4 protocols: an asynchronous DKG protocol, an asynchronous consensus protocol, a weak verifiable proposal election protocol, and a verifiable gather protocol. We discussed 3 of those protocols: the DKG, consensus, and proposal election. And for more details, you are welcome to look at the full paper. Thank you very much.